Okay, physics, here we go again. This time we're going to talk about motors and other applications of that Philby force. So we saw that when you have a coil of wire, you run a current through it, the magnetic field generated by the electric current in the coil teams up on the inside of the coil. So you get a really strong magnetic field inside the coil, effectively creating a electromagnet. And you guys can check that this obeys the right-hand rule. So the part of the coil that's carrying current out of the page, stick your thumb towards you and your fingers should curl like so. And along the bottom there, the current that's going into the page, that's hard to manipulate your thumb in that direction, but your thumb pointing into the page, your fingers will curl like that. Now that's just an electromagnet. That's not Philby yet. So what we would do is we would put that whole setup inside an external magnetic field. So when I do that, I have this field created, this magnet here, external magnet, generating a field north to south, my permanent field, and this magnet here is created by the current. Now what's going to happen there, just like if you put a compass in an external magnetic field, the compass needle aligns itself with the field. It spins around and points in the direction of the field. Also will this electromagnet, so the north side will be pulled down and attracted towards the south side, and the south side will be pulled up and attracted to the north side. So there'll be a twisting that happens. How can we use that? Well, that exact kind of scenario is how we build one of these. You'll remember one of these ammeters from year 11 physics, and you shove some electric current in there, and that little needle deflects around like so. So how does that work? Well, on the inside of an ammeter is a coil, and you connect the ammeter in series, and current flows around the coil. And the effect of that is, this will be hard for me to draw in 3D, but you have, a magnet. It's a magnetic field such that it's sort of like you have a north here and a south here. And so that once you run a current through, it's then a torque is generated and the north is pulled around to the south side, the south is pulled around to the north side, and this whole thing is twisted. And it has to fight against this spring. And the more current, the more you're going to deflect. And then when you take the current out, it's going to go back to zero. That's an ammeter. It could also be a voltmeter, depending on how you set it up. Okay, so we can deflect little wires and coils. Is there anything else we can do? Well, yeah, if we make a slight modification to that setup, we can do something rather revolutionary. So I just showed you how that this setup gets, a torque will bend this around here, and this will get bent around there, and it'll rotate 90 degrees, and it'll get to there. Now when it gets there, it's going to get stuck there because the north here will be attracted to the south will be attracted to the north. There's no incentive for it to move. It's now aligned itself with the external field, it's happy. But if we apply a little engineering trick and we flip the current in this field right there so that this now becomes a south pole and this becomes a north pole, something cool is going to happen. It looks something like this. Flip, and now I have created a situation where the torque on the coil is sort of always in one direction. It's not always strong, but it's always in one direction, so I've created a situation where I have continuous rotation. Hence, I've created an electric motor, and that's a pretty big deal. This is the most sort of simplest way to depict how electric motors work. They are a coil in an external magnetic field. Importantly, there is this ring, a split ring. It is literally called a split ring commutator. It's going to do the job of reversing the current at that critical time. So I want to take this picture and I want to kind of make it simpler and go sort of slow motion through how this is going to work. So I'm only interested in the branch of the coil that is traveling perpendicular. So I'm interested in this branch and this branch, because only those two branches of the coil are going to be taking a current that is perpendicular to this external field. I do not care about this branch here, because that's one of those cases where if I put my fingers in the direction of the field and my thumb in the direction of the current along that branch just there, my thumb's going to close down and be in the same direction as the field, and there'll be no force on that one. The only forces will be on this one. So I'm only interested in them. So let's have a look and see what happens. All right, well, if you put your fingers to the left and you put your thumb for this guy into the page, your palm should be orientated upwards. There's an upward force on him. And for this guy, if you put your fingers to the left and you put your thumb coming at you, your palm should be going down because he experiences the downward force. So what? Now there's a torque, right? Now there's a torque about this axis in the middle. And so that thing is going to rotate. Rotates a little bit. Let's double check. Is everything still the same? All right, if I put my fingers to the left and my thumb into the page, that's still a force up. Fingers to the left, thumb out of the page, that's still down. But the torque here is not as efficient. Why? Because I have this angle that's not 90 degrees. Only a component of that force is actually going to create rotation. The other component, the red one, is just stretching the coil. It's not creating any rotation. So we'll keep going. And then I get to this point here. Again, the force hasn't changed direction. My fingers and my thumb are still in the same orientation. So now the Philby force is just stretching the coil. And so that's not going to help me build a motor. And so the little engineering trick I do is to flip the current at this point. And now the force would be in the opposite direction. Now that's still not creating any torque, but the hope for a DC motor is that it'll have just enough momentum to swing past that point. And now that I flip the current, the torque is helping it along again. And so I have this continual motion. Now, a good DC motor will have more than one coil. So this is just one coil. It would have a couple coils. One like that, maybe one like this, maybe one here. And instead of having a split ring commutator, it's going to have a very complicated commutator, and it'll only send current through the coil that is orientated like this. Sort of the plane of the coil is parallel to the field, because in that case, the Philby force is providing the maximum amount of torque that is at right angles. And so they just activate the coil that is currently in that orientation. Oh, and that's what it looks like. Very pretty, very awesome, cool. So you can sort of see how the split ring commutator is going to flip the current, drops out right there when the coil is at that critical point and reverses the current. So basically, on the left-hand side here, current is always going into the page, and on the right-hand side, current is always going out of the page. That's the idea. Another GIF showing you the same thing. Now that's a real one. And you can see right there's the connection point. And so there's probably going to be, what would there be? Another connection point here, I would assume, so that both of those sides are activated, and there's a coil that runs around like that, probably. Now they have many loops on that coil because that gives you more current, and more current gives you more force. That's a DC motor. My favorite application of the Philby force is this one. A loudspeaker uses that Philby force in an ingenious way to recreate and amplify music. It turns an electrical signal into back and forth kinetic energy. And the setup is, it looks, when you first see it, it looks tricky, but it's actually something you guys can understand. So you have a coil, which hopefully you're familiar with now, that current spins around. The magnet on the back of a speaker is a little bit complicated. You have a north in the middle and south on the outside, so the field goes upwards. The field is always moving away, if you like, from the center point. So in this cross-sectional diagram, let's say the current is coming in here, and so it's going in on every branch of that coil. So if you put your fingers upwards for this blue magnetic field here, put your fingers up, and then orientate your thumb into the page, your palm should be pointed to the right. So there is a force to the right. What about on the bottom? So that current would go, into the coil and swing back out the other side. So current's coming out here, because it's the same circuit. Now if you orientate your fingers downwards and your thumb towards you, again, there's an outward force. And so every part of that coil is getting the same direction of force. If the current flipped, it goes back the other way, then of course the force would flip it. So it would push the speaker in and out as this oscillating current comes in. Thus you can recreate the sound signal with back and forth movement and turn it back into a sound wave. Very, very, very cool. Slow-mo, that's what it would look like. Yeah, super, super awesome, and that's what allows us to recreate music. You guys have a bit of work to do. You should have a look at 5.3. You should be able to do the motor questions there. Use the formula from SCARSA formula sheet. They have a sneaky little formula to help you there. Don't forget to hit like and subscribe. Just kidding, I could care less about that. Happy quarantine, guys.